Welcome to Spring LIB.
Okay, so we're doing chapter 29, problem 57. Cool. So what we have here is we have a long infinite wire up top with a current in the positive x direction here. And a distance d away from it, we have a rod, a metal rod, of length L, and that is point A is the one closest, the end closest to the rod, and B is the end farthest away from the wire. And we have, say it's moving at a speed v in the positive x direction. Okay, so what we want to do now is find the EMF induced on this. So to do this, we know that EMF is given as VBL, but B now is dependent on R, right? So we just have to, we're gonna have to integrate this with R being pointing from the wire down the rod. So this is our differential, and if we're trying to find the total, we know we just integrate this. To do this, we'll have to figure out what B of R is. And B of R around a wire, we've used in some other problems, that's given as mu naught times the current through the wire all over 2 pi times the distance away. So we can plug this in now, and we see that this is going to be integral from d to d plus L, because that's how we're starting. The point A is when the wire starts, so that's d away, and then d is where we end, which is d plus L away. And now we just plug in our stuff, and this was mu naught IV over 2 pi r dr. Cool. So most of that is constant. This is just a 1 over r integral, which comes out to be in the natural log. So this is mu naught IV over 2 pi, and then natural log of d plus L over d. Cool. So that's part A. So now for part B, we want to figure out, does point A or point B have a higher potential? So let's think of this about the magnetic force on the positive charges in there. So the magnetic force is given as QV cross B. So for a positive charge, we have V, which is to the right, and B, which is into the page. So if we do that cross product using the right-hand rule, we should see that FB, for a positive charge, points up, which also means that FB for a negative charge would be the opposite and point down. So if our positive charges are pushed upwards towards A and our negative charges are pushed towards B, that means A is at a higher potential. Cool. So now, for part C, it says if the coil is circular, oh, sorry, that was the wrong question. So it says, what happens now if we replace the rod with a loop of wire or a circuit? So now instead of a rod, we're going to have a loop here that is moving at B. So now, for a loop, we know that Faraday's law says that EMF is the change in magnetic flux with respect to time. But now, the B is constant with respect to time because there's no change in current. If so, B is constant. The only other thing to get the flux is the area. If our area of the loop is just moving along, this is also constant. So that means there's going to be no induced EMF. It's actually going to be 0. So nothing is looped, or nothing is induced because the time derivative of the flux is 0 in this case. So no current, no EMF, no nothing.